guidance. So let's take a look at chemistry and this idea of quantum chemistry. It's not really going to be like when you're going, movie and they just throw around the word quantum all the time, but looking at this idea more, digging into electron configuration that you may have covered, particularly in year 11. So we're going to start off with this idea of orbitals. So we've got these different energy levels that electrons can have around an atom. So we've got these major energy levels, which we call shells, and then we also have these subshells. So we've got S, P, D, and F, each of which can only hold a certain number of orbitals. Then each orbital, which is at a particular energy level, can hold 2 electrons. And so it might only have 1 in it because it doesn't need to be holding 2 at any time, but a maximum of 2 electrons in any given orbital. Total number of electrons you have per shell is 2n squared, so know that our first shell is 2, and then we go on to 8, and we continue getting larger. What we're going to be looking at, or at least part of what we're looking at in this idea of subshells, is why it is that our S subshell only holds 1 orbital, why it is that our P subshell has 3 orbitals. We're not going to focus too much on D and F, but we're going to be digging a bit more into the why. So just in case I was a bit unclear for anyone, when we're looking at these orbitals, that still works within that kind of shell system, but in terms of the graphical representation, it's a bit different. So you can see that S orbital has that spherical shape, and that P orbital is that more polar orientation. So we're needing to look at that 3-dimensional space. Here it's shown broken apart, but in reality, we have this shaded region where we can expect the electrons to be 95% of the time. That's all going to be centered around where the nucleus is. You do want to make sure that you know how to write electron configuration. So again, for some of you, this may be thinking back to year 11 or to previous studies where you're going, all right, 1s2, 2s2, 2p6, 3s2, and needing to continue along in that way. They absolutely can, and very likely will, ask you to write the electron configuration of a given atom or ion. A trick you can use when writing condensed electron configurations is to take one of your noble gases, and then you write that in the square brackets. And so when you do that, you're saying, okay, well, the electron configuration of this, and then you just add on the extra bits belonging to your particular atom. So when we're writing it in the expanded form, it's going to look something like this, but if we wanted to, we could condense that by using our different noble gases to write the condensed electron formula. So if you just Google the electron configuration of something, it probably will give you that in the condensed form. Rather than just writing them out on a page, we also want to start to get the idea of electron configuration in terms of the energy levels, and so we're looking at drawing out these orbital diagrams. So generally you want to be expected to do one this big, and often they might have 2p in the middle and then kind of show them on either side rather than branching out to the right. But you really want to note that down the bottom is where we have the lowest energy, and then you work your way up. So we have different principles that we need to be following when we're filling out our diagrams. And you will be expected to know, the name of these and what they mean, as well as being able to actually apply them in the diagram. So we've got the Aufbau principle, which is where electrons are filled into atomic orbitals from lowest energy to highest. So really, you're working your way up the page. Then we've got Hund's rule, where every orbital in a subshell is singularly occupied before any orbital is doubly occupied. So when you're writing it out, if you look at that 2p level, for example, you would need to put 1 in each of those 3 before you double up in any of them. Then you've got Paul's exclusion principle, which says that no 2 electrons can have the same quantum number. We're going to go into the different quantum numbers and what that means when we're talking about that. But essentially what that's going to mean is you can't put 3 electrons on one line. You can only have 2 electrons in any orbital, and they have to have opposite spin. So you'll do one as an up arrow and one as a down arrow. So when we look at these quantum numbers, we have a few different ones to be aware of. There's the principal quantum number, n, which is describing the size of the orbital. So this is all about what you would kind of normally think when it comes to how our electrons are arranged in their different shells. For this, you're going to have positive integers only, so like 1, 2, 3, 4, 5, 6, continuing up. Then we're introducing a couple of new concepts. So we have the angular quantum number L, which describes the shape of the orbital. Essentially, this is telling you, is it an S, is it P, is it D, is it F? So for this, the integers are between 0 and n minus 1. So you'll note that when we look at our first shell, our first electron shell can only hold 2 atoms. It only has that s orbital, and we're told that again here in terms of there's only one angular quantum number. So it looks like there's a typo in there with the 0 for spherical. Then we've got the magnetic quantum number, m, which describes the orientation of the orbital. So these are integers between negative L to positive L. So depending on what type of orbital shape we have, you have a wide range in how many different options you have here. Then finally we are looking at the spin. So arbitrarily this is kind of set to 1, there being plus half and minus half. The really key thing is that it's 2 different options, which is why we can have 2 electrons in the one orbital, because even if everything else is the same, we can differentiate them by their spin. So my question here is, how can we explain that the s orbital, we can only hold one orbital, so we can have a maximum of 2 electrons in there, whereas something like P can have 6 electrons due to having 3. Don't worry about getting it wrong, just take a guess, and if the answers coming up are really like, showing that you're not sure of what the answer is, I'll go through and I'll explain this again a bit more slowly, go over it a bit more, because it is new concepts. Right, great, we've got our first answer in. Right, so if we think about this, the s orbital, if we go back to that picture of it before, it's a sphere. Right, so we can't really orient it in a different way. And that's reflected by the fact that we only have one number that we get out when we look at the number of possible orientations. Because all quantum numbers need to be unique, we can't just double up and add an extra orbital in that has all the same properties. We would need there to be something different. And so we can fit 2 electrons in because the 2 electrons can have 2 different possible spin values, which means that they can still be unique because we'll just give them a different spin even though everything else is the same. So the really important ones here are the all quantum numbers needing to be unique, and which then plays in with the fact that we get 2 electrons because there's 2 possible spin values. and that we only have one possible orientation, and we only have one number when it comes to what the s orbital can be for a given principal number, right? For a given shell that it's in. So all of the options contribute to this. This is the best answer on here. So when we fill out an orbital diagram, usually it's not going to be in that circle, it'll be more the straight line, but we have this up arrow, down arrow to indicate the different spins. You want to fill in one subshell at a time, starting with one electron in each orbital with the same spin, right? And then work your way from low energy to high energy until the amount of electrons is what's required for your atom or ion. So if we look at this and I was filling it out, I would fill in 1s first, up arrow, down arrow, then 2s, up arrow, down arrow. Then when I go into 2p, I would go for each orbital, like up arrow, up arrow, up arrow. And then I would fill in the down arrow, down arrow, down arrow. Right, so just be careful with the order in which you fill this out. Make sure that you're very careful to be the same as examples you're given. I would recommend really not changing things, because even if it seems like, it's a bit arbitrary, you'd really want to be quite confident before you made something different from like a sample diagram. And then my question that I have here is, without being told or looking at, the link from the file, how could you figure out what atom this orbital diagram is for? Right, so imagine you've got access to the periodic table. Right, so we're seeing some answers coming in here. So yes, we absolutely can count the number of electrons. We just count our arrows, check the periodic table for which atomic number it matches. Could throw us off a little bit if it's an ion, which is why technically I put guess in there instead of being like no for sure. But absolutely that's the approach that I would take. There's also another thing that you could look at. Yep, count the electrons, match atomic number, absolutely. There is a kind of fast way. You don't necessarily have to count all of the electrons. Right, so this is starting to get a bit close where we're looking at the fact that we've got this 4 here. So I'm assuming SF, just a bit of a typo. If we look at the fact that its last one there is that S, and it's got one electron in that, that's telling us it's a group 1 element, and then we look at that 4, and we can see the period. So we could also identify it quickly that way, instead of counting up each individual electron. But either technique will work. An important thing is that we do have exceptions to our usual electron configuration. if you think back to that kind of original orbital diagram, sometimes the lines look pretty close to each other. And so that means that they have a similar energy level, and we have a more stable configuration in the D shell if it's either half full or completely full. So that stability is associated with a lower energy level, which then means that we're going to be filling up our orbital in a slightly different order. So sometimes an electron will move from one shell to another, from 4s to 3d, in order to make that D shell more stable, because there's a very small energy difference between the 3d and the 4s orbitals. So chromium, you might think that it's going to have, so here it goes up 1s2, 2s2, 2p6, 3s2, 3p6 like we'd expect. Instead of going 3d4, 4s2, we've got 3d5, 4s1. Right, so as we're filling it up, we want that 3d5 so that it's half full, even though that means that we have to tweak things a little bit. Same thing happens with copper essentially, except this time instead of it being about it being half full, it's about it being completely full. So our correct configuration for copper, we have 3d10, 4s1. So let's have a look at what these orbitals might look like. Imagine you've got your nucleus in the center of those axes. So if we're drawing out our p orbitals, it will look like this. We've got our 3 different orientations. We can also refer back to the quantum number of 1, and we know the orientations go from negative L to L, so that's negative 1, 0, 1, which gives us those 3 orientations. So again, we can link back those quantum numbers to the results that we actually see to explain why we have 6 electrons in the p orbitals. Now the neat property when we're looking at this is to then apply it across to our visible colours. So when our atoms are heated, they can produce light, which is made into an emission spectra, and we've got our unique emission spectra. We've got electrons absorbing energy, can jump to a higher energy level, the excited state. So if you look at the electron configuration and it seems incorrect, it's not following the Aufbau principle, we've got things at a higher energy level before filling up the lower energy levels, that might be because it's been excited. This is unstable, so the electrons are going to return to the ground state where they're at those low energy levels. In this process, when we've got that energy release, and we're releasing energy in the form of a photon. So we've got our photon emission, and then the energy of the photon we can use to find the frequency of the photon. So the energy gap between the orbitals tells us the energy of the photon that's released. So that's what's responsible for our different colours we get in flame tests. And we can see this example with sodium here, where we have our 3s electron jumping up to 3p. And there's going to be multiple different possible excited state configurations depending on how much energy is absorbed. We can use this to predict what colour a metal is going to produce when we heat it. So we know that the emitted photon will have some energy level. That energy level will be Planck's constant, which is just a number, multiplied by the frequency. And the frequency of light tells us the colour. So when we're looking at this, a couple of things to be wary of. Planck's constant comes in 2 different versions. We've got the electron volts version and the joules version. These are different numbers depending on what units you're using. Make sure you pick the one that matches up with the energy you're given. So if you're given energy in joules, use the version of Planck's constant. This is the one starting with 6, that's in joules. If you're given it in electron volts, then you want to make sure you use the electron volts version of Planck's constant. So a question on that might look something like this, and then if it was something with a visible colour, it might present you with a colour wheel. So here we're told a hydrogen atom has an electron transition from an orbital with energy 12.8 electron volts to 10.2 electron volts. We're just going to take our 12.8 minus 10.2, and that tells us that the energy difference is 2.6. Now we're told that Planck's constant is 4.14 times 10 to the negative 15 electron volt seconds. Okay, so we're using the correct version here, and we need to know the frequency of the emitted atom. So E equals HF, quick rearrangement, E, and then we're just going to divide that. Again, as per usual, just make sure you're careful with brackets on your calculator. And then you'll get out, in this case, that we have 6.28 times 10 to the 14 hertz. So that was our kind of calculation example. Now I have a question for you. In a flame test, copper is observed to produce a blue flame, whereas lithium produces a red flame. Which metal emitted higher energy photons? Great, first answer in. Right, I'll give you a quick look at what the answers are looking like before we go back to seeing this. Okay, so I'll start to talk through the steps of this. We're comparing a blue flame versus a red flame. So we look at our visible spectrum and we can see that blue is higher frequency and lower wavelength compared to red. We know from our equation before, E equals HF, that higher frequency is associated with more energy. And so we're going to use that to then go, well, since the blue is a higher frequency color, it's got more energy, and therefore it's the copper that has produced the higher energy photons, as has been indicated here. Right, so good job for everyone.